Suppose you're given following data set, this one right here. This contains three features: outlook, humidity, and wind speed. Based on that, a person, either he goes outside either to play or not to play. Your job is to construct a decision tree that would decide, based on these three features, your outlook, humidity, and wind, whether that person is going outside to play or not. Now, decision tree, they fall under supervised machine learning algorithm. They can be used for both classification and regression. So classification problem would be like where you're trying to predict the category. Maybe something is yes or no, or maybe more than one classes. For example, you're trying to predict whether something is apple, or maybe it's a banana, or maybe it's a guava, things of that kind. Regression, on the other hand, it refers to when you're trying to predict a numerical value. Maybe you're trying to predict the numerical value of a house. What is the cost of a house? Now, let's take a look at some of the examples of decision tree that we use in our day-to-day life. Suppose you have to decide whether you're going to play outside or not, and you decide based on two features: humidity and temperature. Now, humidity, it can be high or normal. Your temperature can be cool, mild, or hot. So you ask yourself a series of questions. You ask yourself, how's the humidity? If it's a high, then you are not going to play outside. The answer is no. If the humidity is normal, then you're going to ask, what is the temperature? If the temperature is mild, then you're going to say, yes, I will play. If the temperature is cool, you're going to say, nope, I'm not going to play. If the temperature is hot, you're going to say, no, I'm not playing. This one right here, this is called a root node. This one right here, the one at the bottom right here, these are called your leaf nodes in decision tree terminology. Right here, this is a leaf, this is a leaf, and this one is also a leaf right here. These right here, they are called branches right here, all these. Now, this is another example of a decision tree. Here, I'm trying to decide whether a person has a risk of heart attack or not. Maybe he's a low risk or a high risk. So my features in this case are age, weight, and smoker. So your root node, it starts with age. It asks, what is his age? If his age is less than 18, then you ask this question. What about his weight? What is his weight? If weight is less than 60, then he is at a low risk of heart attack. On the other hand, if the weight is more than 60, then you're going to classify this person as a high risk. Age, if it's between 18 and 30, then you're going to classify this person as a low risk. On the other hand, if the age is more than 30, then you're going to ask another question. What about the smoker? Is he a smoker or not a smoker? If the answer is no, he's not a smoker, then you're going to classify this person as a low risk. On the other hand, if he is a smoker, you're going to classify them as a high risk. These right here, these are your leaf nodes. This one, this one. These right here, these are referred to as your your nodes or your decision nodes. And this one right here is called your root node. Root node is always on the top. And there's another terminology that you should be aware of, is a depth. So this branch right here, this is one depth and this is two depth. So this particular branch right here is depth 2. This particular branch, this has only depth 1 because there's only one branch. This one has 1 and then 2. So this particular branch is depth 2. Right? Likewise, this particular branch right here is depth 3. Now, how do you construct a decision tree? In this, I'm going to show you the algorithm that is used to construct decision tree. Here, we are going to construct a decision tree from training data. Step number 1, you choose the best attribute. So the algorithm, it goes over all the features and uses a metric such as your Gini impurity, entropy, or maybe information gain. And what it does, it finds the feature that best separates these classes, and that becomes your root node. That's your first decision. That would be this right here. This is my root node over here. Step number 2, now you split your data set. So the data set is divided into groups based on the selected feature, the feature that you selected over here. So if you're using a numerical feature, then you're going to use a threshold. For example, in your iris dataset, you may be using something called petal length. You may say that, hey, if the petal length is less than 2.5, then group all this data in this category. If the petal length is more than 2.5, then you group them in a different category. Now, on the other hand, if you have categorical features, in this case, your data would be split by categories. For example, your temperature, it could be hot, mild, cold. If your temperature is hot, you put them on one side. If your temperature is mild, you put them on the different group. If the temperature is cool, you put that data set in a different group. And then you repeat this process. For each new subset of data that you get, you keep applying the same steps over and over and over again. So you choose the best feature, you split your data, and you create new branches. So if this is your root node right here, you actually go like this based on some decision. And let's say this is one branch, and you split like that, and you keep going, you keep splitting, keep splitting until some stopping criteria or stopping rule is reached. So these are some of the stopping rules. Number one, maybe all the samples in a node belong to the same class. So once you reach this, like let's say all the samples over here in this particular node right here, they all belong to the same class, you stop. Or maybe you can say that no features left to split. In other words, you have used all the features. Or maybe maximum depth is reached. So in this case, your depth would be 1, 2, 3. So in this case, you can specify that if my maximum depth is 3, then stop. Don't go beyond that. Or maybe you can say minimum samples per node. For each node right here, you want minimum number of samples. So you can use either one of these criteria to stop your recursive process. Now, let's understand a few terminology that is used in decision tree. The first one is entropy. It measures the randomness in your data. And this is the formula that is used to measure the entropy for a data set. Here my S, it refers to your data set. Your K, it refers to the number of classes that you have in your data set. And your PI right here, they refer to the probability of class I in the data set. So let's understand this formula through a simple example. Suppose we have two class, plus and minus. So my I equal to 1 is plus and say my I equal to 2 is minus class. Then this formula right here, it will become something like this. Your HS equal to minus summation I equal to 1 to 2 because you only have two classes, so I'm putting 2, and your PI log PI. So in this case, my P1 would be the probability of class 1, which is how many fractions of plus you have, and P2 would be the probability of class 2. In other words, how many fractions of negative you have. In this case, you can determine your P1 would be equal to, well, in this case, you have 1, 2, 3, 4, 5. There are 5 divided by the total count is 10, so it's going to be 5 over 10. And your P2 in this case is going to be, in this case, there are 5 negative, so it's going to be 5 over 10. So in this case, they happen to be same. So let's try to understand this randomness through some examples. I have this 4 examples. This is my first one, second, third, and fourth. And if you look at these pictures, here you have more randomness. You have like 50-50. 50% are plus and 50% is minus. Over here, there are like 1, 2, 3, 4, 5, 6, 7. 7 are plus, only 3 is minus. So here randomness is low. Over here, you have 9 pluses and only 1 minus. Randomness is way low over here. And in this particular case, all of them are plus. There is absolutely no randomness over here. So let's calculate the randomness of this. So I'm using that formula right here. I'm just substituting my P1 and P2. In this case, my P1 would refer to how many pluses I have in this case, or how many fractions of plus I have. In other words, what is the probability of obtaining a plus? In this case, it's going to be 5 over 10. And likewise, the probability of minus would be 5 over 10. Substituting your value, your answer comes out to be plus 1. Your randomness in this case is maximum. So your plus 1 is the highest number. Let's look at this case right here. I'm using the same formula right here. In this case, my P1 would be the probability of getting a plus. Well, how many plus do you see over here? 7. 1, 2, 3, 4, 5, 6, 7. So it's 7. 7 divided by 10, that's going to give you the probability of 7. Probability of plus, and likewise, probability of minus would be 3 over 10. So this would be 3 over 10. Substituting your value, your answer comes out to be 0.8812. Let's look at this one right here. Here, I have 9 pluses and only 1 minus. So in this case, my P1 is 9 over 10 and my P2 is 1 over 10. Substituting your value, your answer comes out to be 0.469. And in this case, all the values are plus. There is no minus. So in this case, my P1 is 10 over 10 and my P2 is 0 over 10. In this case, my entropy is 0. So you can see that your entropy is ranging from 0 to plus 1 for the binary class, only for the binary class. So in this case, my entropy went from plus 1 to 0.8812 to 0.469 to 0. So it went down, and you can see that as your randomness is becoming smaller and smaller and smaller, your entropy is going down. Now let's calculate the entropy of these two data set. First one, and the second one. Now, in the previous case, we only had two classes. Over here, we have three classes: red, green, and blue. Substituting your value, in this case, my k equal to 3, substituting your value, expanding the expression, you get this expression right here. Now, your P1 refers to probability of red. The probability of red is going to be 4 over 12 because there are 4 reds and total is 12. And same thing, probability of green would be 4 over 12 because there are 4 greens and the total is 12. And same thing with your blue. So substituting your value in there and you will get this answer, which will be 1.585. So that is your randomness, the entropy. Now let's do the example 2. In this case, I have 1, 2, 3, 4, 5, 6, 7. I have 7 red. So my P1 is going to be 7 over 12. My P2 is the probability of getting green. That will be 2 over 12 because there's only 2 green. And the probability of blue would be 3 over 12 because there is only 3 blue. Substituting your value, your entropy will come out to be plus 1.384. Now let's understand information gain. Information gain is defined as the entropy before the split minus entropy after the split. Entropy before the split, that is the entropy of the parent, and the entropy after the split, that would be the weighted entropy of the child nodes. This information gain can also be written in a mathematical expression like this right here. In this case, my HS, this right here, this is my entropy of the parent, and this right here, this is the weighted entropy of the child node. Let's understand this crazy looking expression through an example. Suppose that your S is split into 3 child nodes right here based on the attribute A, in other words, based on the feature A. So this is S1, S2, and S3. So these are the subsets of your set S. Then the formula for IG in this particular instance would be the entropy of your parent node, that is entropy of this right here. So this would be HS minus size of your S1. So let's say the size of this S is 10, and let's say the size of this is 5, this is 1, and let's say this is, actually let's make it 4, and let's say this is 1. So in this case, your size of S1 would be 5, and the size of your S, that would be 10, times entropy of S1 plus size of S2, in this case size of S2 is 4, divided by size of S, that would be 10 again, times entropy of S2 plus size of S3, in this case size of S3 is 1, divided by the size of S, in this case that would be 10, times entropy of S3. So this is the expression for information gain when you split S based on the attribute A into different subsets. So let's understand this information gain through an example. Suppose you're given this data right here. This one has a feature like weight, shape, and sweetness. And this is your label right here, is banana, whether it's a banana or not a banana. And using this data, you have to construct a decision tree that would decide, based on these features, your weight, shape, and sweet, whether it's a banana or not. So at any node, you have to determine which out of these 3 features, which feature to use when splitting. Here, just by looking at this, you can tell that your shape is the best feature. If something is round, like this one, this one, this one, this one, these are not banana. Round, not banana. On the other hand, the ones that are elongated, these are your banana. So you can tell, you can see that just by looking at this. Now let's see if we can determine this using our formula for information gain. Now let's calculate the information gain when we split along the feature suite. Let's change the color of the pen. All right. So in this particular instance, I have 5 bananas and 5 not bananas. These right here. So this is my parent right here. Now when I split this based on the suite characteristic, I'm going to get 2 options, yes and no. So in the yes, you have this one, yes, 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 and yes. Among these yeses, how many you see? 1, 2, and there's one more yes right here. Among these yeses, 2 of them are bananas, which would be this one and this one. These 2 are bananas. So this is how I get these 2 bananas over here. And among those yeses, 3 are not bananas. You can see that this one is not a banana. this one is not a banana, and this one is not a banana. So you have three not bananas and two bananas in the yes side on this child. So this is my left child. Now let's look at the right child. In the right child, that would be under no category. So how many no's you see? Well, there is this no, one, and no, 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 and no. Now, among these no's, three are bananas. You can see that. This one is banana right here. This is a banana, two, and this one is another banana. So there are three non-bananas. Sorry, three bananas, which that would be this one, and two of them are not banana. So in this case, let's look at the no category. No, in this case, this is also no. This is not banana. All right, and yeah, this is also not banana right here. So two of them are not banana. Okay, now we find our information gain using this split right here. So formula for information gain is this right here. This I actually got it from this expression right here. So h of parent minus the size of your left child divided by the size of your parent times entropy of your left child plus the size of your right child divided by the size of your parent times entropy of your right child. All right, so let's calculate our H parent first. In other words, the entropy of your parent. This is the expression, this is the formula. Substituting your values in there. In this case, my P1 would be probability of banana, P2 would be probability of not the banana. In this case, you can see your parent actually has 5 bananas and 5 not bananas. So it's going to become 5 over 10, 5 over 10 for each one of them, and the answer will come out to be plus 1. So this is the entropy of the parent. Now let's calculate the entropy of the left child. That would be this one right here. So in this case, same expression, substitute your values. Now in this case, my P1 would be the probability of banana. In this case, probability of banana is 2 because there are 2 bananas right here. Okay, so this is how you get 2 over 5 because there are total 5 in this case. Likewise, probability of not banana would be 3 because there are 3 of them that are not banana. That would be this right here. So substituting a value 3 over 5 in there, and your answer comes out to be 0.9709. So this is the entropy of left child. Now let's calculate the entropy of the right child. Well, in the right child case, you use the same expression again, right here, this here. Now you substitute the value of P1. P1 would refer to the probability of banana. In this case, there are 3 bananas. You can see that. 1, 2, 3. 3 bananas, and out of these 3 bananas, uh, 2 of them are not banana. So you substitute 3 over 5, 2 over 5 over here. That comes from here. Substituting your value, your answer comes out to be exactly same 0.9709. So now I know my entropy of my child, and I also of my left child, and I also know the entropy of the right child. Let's change the marker color. All right. Now substitute your value of h parent and on all these values inside your ig, which is inside this expression, and this one comes over here, and the answer comes out to be 0.029. So this is the information gain when you perform a split along the feature suite. Now let's look at the information gain when we split along the feature weight. So I'm using this criteria, weight greater than 0.3. So in this case, if weight is greater than 0.3, I'm going to go in this direction on your left child. Otherwise, I'm going to go on a right child. This is my right child. So let's see how many of them have weight greater than 0.3. Well, I have this one, this one, this one, this one, this one. Now, among these 5, how many are bananas? Well, let's see. You have 1, 2, 3, 4. 4 bananas. And this is how I get 4 bananas over here. How many of them are not bananas? There's only one. This one right here. And this is how I get 1 not banana. Okay, now what about the other one? Well, weight greater than 0.3. What if it's no? Well, in this case, you can see that this one is not, this actually satisfies that condition. This one, this one, this one, and these ones. So these 5 are the ones where weight is not more than 0.3. How many of them are bananas? Well, in this case, there's only one banana, this one right here. This is why I get 1 banana over here. How many are not bananas? In this case, there will be 4. This one, this one, this one, this one. These 4 are not bananas. Okay, so this is how you get it. Assuming that you understood this now, let's calculate our information gain. So this formula is exactly same as the previous one, except now I'll be changing some of the values. My entropy of my parent, that is same as the previous one. Nothing changed over here, so this is plus 1. Entropy of my left child. So let's focus on this one, left child. This is my left child, and this is my right child. Now, entropy of my left child, putting in the values, expanding your expression, and putting your values of P1 and P2. P1 would refer to the probability of banana. In my left child, that would be 4 over 5 because there are 4 bananas and total is 5. So it's going to be 4 over 5. P2 will refer to the probability of not a banana. That would be this right here. So probability of not a banana would be 1 over 5. And substituting your value, the entropy for your left child comes out to be 0.7219. Likewise, you can calculate the entropy of your right child, which is right here. So expand this expression, put in a value for P1 and P2. In this case, my P1 would refer to the probability of banana. There's only one banana, so it's going to be 1 over 5, 1 over 5. And probability of not a banana would be 4 over 5 because this is 4 right here. So it's going to be 4 over 5 and 4 over 5 over here. Substituting the expression comes out to be this answer. Putting these values inside this left child, the size of your left child, entropy of your left child, size of your right child, entropy of your entropy of your right child. Putting in these values, you will get this number right here, 0.2781. So this is the information gain when you split along feature weight. Now let's look at the information gain when we split along the feature shape. There are two types of shape, round and elongated. So if the shape is round, let's count how many rounds are there and how many of them are bananas and not bananas. In this case, this is my round 1, 2, 3, 4, and 5. Out of these 5, you see there's no banana. Actually, there's none of them is actually banana. So you see 0 banana. Okay, how many are not banana? Well, there are 5 of them. This is not a banana, not banana, not banana, not banana, and not banana. So 5 of them are not bananas. Now let's look at the elongated. In elongated, let me just remove everything. Okay, elongated would be this one, this one, this one, this one, and this one. Now out of these 5, how many of them are bananas? There are 5 of them. These all 5. And rest of them are not bananas. And this is how you get this one. 5 bananas and 0 not bananas. Okay, assuming that you understood this now, I'll be using my information gain, same formula as before. My H parent, which is my entropy of my parent, this is same parent as the before, as the previous one. So this does not change. This is plus 1. In this case, my entropy of my left child, which would be this one right here. This is my left child, and this is my right child. So entropy of my left child would be given by this expression. Expand this expression. P1 refers to the probability of a banana. In this case, there is no banana, so the answer is 0. And same thing with P2. P2 in this case is the property of not a banana. In this case, there are 5 not bananas. It's going to be 5 over 5 log 5 over 5, and the answer comes out to be 0. So this is the entropy of the left child. Now the entropy of the right child would be given by similar expression. So in this case, just expand the expression, substitute value of P1. In this case, P1 would refer to the probability of banana. In this case, there are 5 bananas out of the total 5. So it's going to be 5 over 5. Okay, and this would be 0, and the answer would be 0. Put in your value in there right here, all these values you substitute, and your answer will come out to be 1. This is your information gain from your shape. Now here's interesting thing, this is a pure split. You see that this is 5 not banana, this is 5 banana. This is called pure split because you do not see the other class over here. So when we perform the split using the feature suite, weight, and shape, we notice that our information gain is maximum for the shape. So we are going to be using this as our root node. This is going to be our splitting point right here. Now, since we understand what an entropy is, what is information gain, and how you perform a split, let's create a decision tree for this data set right here. This one tells you the 3 features, outlook, humidity, and wind. Based on these 3 features, a person, whether he goes outside to play or not to play. So this is your label. In other words, this is your response or target variable. This right here is your feature. So step 1, calculate the entropy of your entire data set. In this case, there are only 2 classes, yes and no. Right here, this is my yes and this is my no. There are 1, 2, 3, 4, 5 yes, and there are only 3 no's in this case. So in this case, probability of yes would be 5 over 8, and then substitute your values in there using your regular entropy formula. Your answer will come out to be 0.954. So this is the entropy of the parent. Step 2. Now you compute information gain for each one of these 3 features, your outlook, humidity, wind. that would be these features right here. Okay, so let's start with the outlook first. So in this case, the outlook, there are three types: sunny, overcast, rain. So on sunny, I calculate the entropy, and the answer comes out to be 0.918. The entropy for overcast, well, this is zero because everything is, you can see, just one class. So entropy is zero. In this case, entropy for rain comes out to be 0.918. I'm assuming you know now how to calculate entropy. Now we calculate weighted entropy. So weighted entropy would be this expression right here. This is my weighted entropy. So calculate weighted entropy for each one of these class for this combined together, and the answer comes out to be 0.689. So, and I also know my entropy of my parent. So you know entropy of HS. So substituting these values inside this expression right here, and the answer is 0.954 minus 0.689, and the answer is 0.265. So this is the information gain for this data set when you split along the feature outlook. Now let's look at the information gain when we split along the humidity. So humidity, there are two types: high, normal. So there are two yays and two nays. In this case, my entropy comes out to be 1. In this particular instance, my entropy comes out to be 0.811. So weighted entropy, that would be this formula right here, this one. This comes out to be 0.905. So my information gain when you split along the humidity is 0.049, which I'm actually using this formula right here. Okay, now let's split this thing along the wind, the feature wind. In this case, there are two categories: weak and strong. Well, in weak, we have 4 yays and 1 nays. In this case, your entropy comes out to be 0.722. In this particular instance, you have 1 yay and 2 nays. In this case, my entropy comes out to be 0.918. The weighted entropy using this formula right here, this is the weighted entropy right here. This comes out to be 0.799. So your information gain along this is 0.155. Here, your information gain is maximum for outlook. That would be this right here. So information gain is maximum. That means this becomes your root node. So this is how my decision tree looks like right now. So here I have three options. I have sunny, overcast, and rain. Let's start with this branch first. Let's see what happens over here. So in this case, using your sunny, you split that using humidity. Humidity can be high, it can be normal. For your high, you have 2 nays, and for normal, there's a 2 yays. In this case, your H comes out to be 0. In this case, also your H comes out to be 0. H in this case refers to entropy. You can also see that entropy is 0 because this is a pure. You see, both of them are red, there's no white. In this case, everything is white, there is no red over here. Okay, so weighted entropy comes out to be, in this case, 0. So information gain using this expression right here is equal to H of S, which is H of parent. Now your H of parent, which is this right here, sunny, is given by this expression right here. So assuming that you know now how to calculate entropy of a set, in this case, calculating entropy of this set, the answer comes out to be 0.9235. So it's going to become 0.9235 minus 0, and the answer is 0.9235. Well, this is going to be maximum because your weighted entropy is 0. Since your weighted entropy is 0, that means your information gain has to be maximum. So this is my splitting point. So now this is how your branch looks like. You have sunny, and over here I split on humidity, and so this is your leaf, this is your leaf. Now let's look at the outlook. In this case, your overcast, both of them are pure. Both of them are yays. In this case, there is no nays over here. So this is a pure one. So in this case, there is no split needed. Overcast is pure. So this is a leaf. Now we split the data set on this branch. Outlook, rain, this one right here. Okay, so let's focus on this one now. So here I have rain. Now calculate your entropy for your rain. In this case, I calculate the entropy for this set, and the answer comes out to be 0.9235. Now I'm asking for the wind now. I'm saying, what is the wind? Is it weak or is it strong? I'm using the wind as a feature. In this case, both of them are yays for weak, and for strong, only one is nay. This is pure. You can calculate your entropy, comes out to be 0 for both of them. So weighted entropy for this one also is 0. So my information gain using this expression comes out to be 0.9235. So information gain is maximum along this branch. So this wind is my splitting feature over here. And now you can see all your splits are done. Your this is pure, 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 pure. There's no further split required. So this is your final decision tree. Now let's look at some of the advantages of decision tree. Well, first of all, they're easy to understand and visualize and explain. You can see that from here. See over here, what I'm doing, you can actually read this way: that if your outlook is sunny, then go this way. If it's a humidity, then go this way. Then you make this decision. So because you're using series of if and else logic, they're kind of easy to explain and visualize. Also, we did not do any feature scaling in decision tree. So that's another advantage of this. It can handle both numerical and categorical data. We also saw that. And it works well if you have missing values, and even if you have outliers exist, they do not disturb your tree much. And they do have a fast training time and prediction time.